Imagine that the two arrows touching each other. What do they look like? Since we are talking about maths, we can say that these two arrows as two vectors. So, an arrow is a real world example of vectors. An arrow has a length and we can say the direction by looking the end point towards which the arrow is pointing. Likewise, vectors also have magnitude and a direction. Now, the thing is, can we perform any operations in these vectors? Just like scalar or real numbers, vectors can be added, subtracted, multiplied, or can even find the multiplicative inverse. So in this session, we focus on multiplication. There are different types of multiplication of vectors. So come, let's explore the types of multiplication and how they differ. Here, we are going to discuss about the product of two vectors. And there are two types of products of vectors. One is scalar vector, which is also called as dot product. Another one is vector product, which is also called as cross product. Now, let's discuss one by one in detail. First, you will learn to find the scalar product of two vectors. So, the scalar product of non-zero vector A and B is defined as the product of magnitudes of A and B and the cosine of the smaller angle between them. As you can see here. And the dot is the operational symbol which we use for the scalar product. Scalar product of vectors A and B can be interpreted geometrically. If a perpendicular is drawn from the end point of vector A onto the vector B, then OM represents the orthogonal projection of vector A onto vector B. Now, consider the right triangle OAM, the ratio of the base to the hypotenuse, that is, OM by magnitude of vector A is what? Cos theta. This equality helps us to deduce that the base of this right triangle is magnitude of the vector A into cos theta. Thus, the scalar product of vectors A and B is the product of the magnitude of vector B and the scalar component of vector A along vector B. Similarly, the dot product of vector B and A can also be obtained by multiplying the magnitude of vector A and the scalar component of vector B along vector A. The dot product of vector A and B can be obtained by either multiplying the projection of vector A on vector B by magnitude of vector B or by multiplying the projection of vector B on vector A by the magnitude of vector A. And this fact helps us to conclude that the dot product of two vectors is commutative. That is, A dot B is equal to B dot A. Now, let us see certain observations one must keep in mind when it is related to the dot product. First one, on taking the dot product of two vectors, we get a scalar result. That means we get a simple number instead of a number and a direction. That's the first point. Second, the dot product of two vectors is the product of the magnitudes, right? If theta is equal to 0. Third one, the dot product of two vectors is equal to 0 when theta is equal to pi by 2 because cos pi by 2 is 0. Another thing is that the dot product of two vectors is maximum when theta is equal to 0 as cos theta will have its maximum value 1 when theta is equal to 0. And this fact helps us to conclude that dot product of the unit vector I cap dot I cap, that is I dot I will be equal to j dot j equal to k dot k is equal to 1. The dot product of two vectors is equal to 0 when theta is equal to pi by 2. From that we can say the dot product of unit vector I dot j will be equal to j dot k is equal to k dot I is equal to 0. And another thing is that when dot product of vectors a and b is given, the angle theta between the vector a and b is given by cos inverse of dot product of a and b by magnitude of a and b. Next thing we have to understand is that the dot product of two vectors is commutative. As we have seen, a dot b is equal to b dot a. The dot product of two vectors is minimum when theta is equal to pi, as cos theta has a minimum value that is -1. This fact helps us to conclude that dot product of two vectors is the negative of the product of their magnitude when the angle between two vectors is equal to pi. Alright? So far we have seen some observations of dot product. Now we will discuss some important properties related to scalar product. And the very first important property is the distributive property. For any three vectors a, b and c, a dot b plus c is equal to a dot b plus a dot c. Next, if a and b are two vectors and lambda is any scalar, then the dot product of lambda a into b will be equal to lambda into a dot b, which is also equal to a dot lambda b. So here you have learned the scalar product or dot product of two vectors. Now we can learn about the projection of a vector on a line. For that we have to consider a figure. Let us consider a vector PQ which makes an angle theta with a directed line L in the anti-clockwise direction. The projection of vector PQ on this line L is the vector P, whose magnitude is the magnitude of P vector into cos theta, and the direction is either positive or negative depending on the angle theta. For theta greater than 0 and less than 90 degree, cos theta is positive. So the vector P has the same direction as a line L. Now when theta is greater than 90 degree but less than 180 degree, cos theta is negative. So in that case, the direction of vector P is opposite to the direction of line L. That means we get a minus factor. But the magnitude of P will remain the same because it's a modulus value. So modulus of P is equal to modulus of R into cos theta. Alright? And this is a figure when theta is negative. Alright. The vector P along line L is called the projection vector, that is P. Now the magnitude of this vector P is called the projection of vector PQ along the line L. Now let's see some observations. If P cap is a unit vector along the line L, then the projection of the vector A on the line L is given by vector A into P cap. Next, the projection of vector A on any other vector B is given by the dot product of A and the unit vector B. Now, the unit vector in the direction of vector B is given by B by magnitude of vector B. So, the projection equals the scalar product, that is A dot B by modulus of B. Now, if theta is equal to 0, then the projection of vector PQ will be PQ itself. And when theta is equal to pi, then the projection of vector PQ will be what? QP. Now, if value of theta is equal to pi by 2 or 3 pi by 2, then the projection vector of PQ will be nothing but it's a 0 vector. Now, let's look at some important points. If alpha, beta, gamma are the direction angle of a vector, then A is equal to A1i plus A2j plus A3k. These are the components of A. Then its direction cosines may be given as cos alpha is equal to A dot I by modulus of A into I, which can be written as A1 by modulus of A. Similarly, we get cos beta is equal to A2 by modulus of A. Cos gamma is equal to A3 by modulus of A. Now, we can rewrite them as A1 is equal to modulus of A into cos alpha, which is nothing but the projection of A along the x-axis. Now, what is A2? A2 can be written as modulus of A into cos beta. So, this is a projection of vector A along the y-axis, and A3 is modulus of A into cos gamma, and which is nothing but the projection of vector A along z-axis. Let's see some examples to make these concepts more clear. You can see here, find the angle between the vectors A is equal to I minus 2j plus 3k and B is equal to 3i minus 2j plus k. Here the two vectors are given. So, we have to find angle. So, we know the equation as cos theta is equal to vector A dot vector B by product of the magnitude of vector A and vector B. So, first we have to find the magnitude of both vector A and vector B. And here, modulus of vector A is equal to root of substituting the value 1 square plus minus 2 the whole square plus 3 square, we get it as root 14. Similarly, we get modulus of B is equal to root 14, substituting the values. Now, we have to find A dot B. A dot B is I minus 2j plus 3k into 3i minus 2j plus k. What we get? We get it as 3 plus 4 plus 3, which is equal to 10, because I dot I is 1, j dot j is 1 and k dot k is equal to 1. So, this is the dot product. We got it here. What is cos theta? Cos theta, we have to substitute the value here. A dot B by modulus of A into modulus of B. Substituting the value, we get 10 by 14 and that is 5 by 7. Or theta is equal to cos inverse of 5 by 7. Now, let's see another question. To find the projection of vector A, I plus 2j plus k on the vector B, 4i plus 4j plus 7k. How will you find? We know that the projection of vector A on B is given by A dot B by modulus of B. So, first we have to find A and B. So, what is A dot B? A dot B, we get it as, taking the dot product, substituting the value, we get it as 19. Now, what is modulus of B? Taking the square root of 4 square plus 4 square plus 7 square, and we get it as 9. Now, substituting the value over here, we get it as 19 by 9. So, the projection of the vector A on vector B is nothing but 19 by 9. Some of you might have experienced twisting a bowl with a spanner. Have you? You may wonder, why am I saying about this example? This is a straightforward example of a cross product. While the direction you apply the force that can be push or pulling the spanner determines one vector and the length of the spanner determines the another vector. The resultant twist direction is perpendicular to both the vectors. And there is no twist if you push or pull the spanner, but you obtain the maximum twist if you push or pull the spanner at a 90-degree angle. This makes it a real-world, straightforward example of a cross product, or it can also be called as vector product. Now, let's discuss the mathematical aspects related to it. For any two non-zero vector A and B, the cross product is defined as the product of the magnitude of vector A and vector B and sine of the angle between A and B and a unit vector n. And here, as you can see, cross is the operational symbol which we use for vector product. And this equation What is this theta? Theta is the angle between A and B where it ranges from value 0 to pi. And n is the unit vector perpendicular to both A and B. Now, let's see some observations related to the cross product. The cross product A cross B is also a vector, which means we get a number along with a direction. Now, what happens when theta equal to pi? The value of sine theta will be 0. So, vector A cross vector B will be 0. And when this cross product of two vectors is 0, then the vectors are parallel or collinear to each other. Next, when theta is equal to pi by 2, we know sine theta will be 1. Then the cross product A cross B is equal to modulus of A into modulus of B. By the above two observations, we can say that for unit vectors, for mutually perpendicular unit vectors I, J, K, I cross I is equal to J cross J is equal to K cross K is equal to 0. Also, for unit vectors, I cross J is equal to K and J cross K is equal to I, and similarly K cross I is equal to J. Now, what about the angle between two vectors A and B? And it is given by sine theta is equal to modulus of A cross B by modulus of A into modulus of B. Next, vector product is not commutative. Why? When theta is transversed from vector A to vector B, the cross product will be A cross B. Now, when theta is transversed from vector B to vector A, the reverse, the cross product will be changed as B cross A. So, A cross B is equal to minus of B cross A. So, we can say that the cross product is not commutative, unlike the dot product. Now, another observation we have to notice that when vector A and vector B are given as adjacent sides of a triangle, then the area of the triangle is found as half into modulus of A cross B. Another, when A and B are given as the adjacent sides of a parallelogram, similarly we can find the area. How? The area of a parallelogram is given by just taking the modulus of A cross B. That means take the cross product, then take the magnitude of that. Right? Next is the properties of vector product. If vector A, vector B and vector C are three vectors, then A cross B plus C is equal to A cross B plus A cross C, or distributive property. Now, if lambda is any scalar which is multiplied with A cross B, then this is equal to lambda A cross B, which is again same as A cross lambda times B. Alright. Next, we will see how we will find the cross product of vectors when the components of vectors are given. See this, we have to take the determinant of vectors. Here we are given vector A. The components are A1i plus A2j plus A3k, and the B vector is given as B1i plus B2j plus B3k. So what we have to do? We have to take the determinant. Let's see that the cross product is obtained as determinant of ijk A1, A2, A3, B1, B2, B3, written like this. Now we have to take the determinant. We get the cross product A cross B. Now here's a question to find the cross product of two vectors. The component of two vectors are given. A is equal to I plus 3j minus 2k and B is equal to minus I plus 3k. So first we will write the components in the determinant form as per the equation which we studied just now. So writing this, substituting the values for A1, A2, A3 and B1, B2, B3, taking the determinant, so on solving, we get the determinant, that is A cross B is equal to 9i minus j plus 3k. Now we have to take the magnitude of A cross B, that is magnitude, we get it as 9 square plus minus 1 the whole square plus 3 square, and we get the final answer as root 91. So the magnitude of cross product is equal to root 91. This is how we calculate the cross product using determinant. Alright? Although the scalar products on their own have its own importance, in practice we use them together with cross products. Along with vector calculus, vector algebra is widely used in engineering, medicine, physics in addition to mathematics. To determine the volume of a parallelepiped, the quantity of work completed, and other factors, in all these fields, it uses the cross product and the dot product of vectors. So, keep exploring and find out more applications. Now, it's time to wind up the section. Let's do a quick recap.
Manorama Horizon. Learning made simple.